Okay, questions?
I just have a question about the exam that's next Monday. Would it be on 1, 2, and then whatever you get?
Yes. So it'll be on general chemistry topics, naming, and then Newman's and chair confirmations. I don't think we'll make it to EZ this week, but we'll start that up at the end. Or we'll start that up on Wednesday next week.
For a question, you are top hat. Somebody understands that chlorine was given a solid wedge.
Which question was that?
Number 8.
Number 8.
5.7.
Oh, there it is. Okay. Okay. So why is this? So how do we handle just the manipulations here of the chair? So, all right. So in order to understand how we can determine which of these is correct, or which of the flat cyclohexanes is what I call them, is the same as the chair, we need to realize that what the positions are in the chair itself. So all of the positions, this position, and as well as this position, those are easy. Are they above or below the plane of the ring? They're axial above, right? So those are axial above. And so the axial positions are relatively easy to see. And the axial positions down are relatively easy to see. It's the equatorial ones that cause a little bit of problem. So my suggestion is that when you're trying to determine if something is above or below the plane of the ring, that if you're looking at this chlorine, for instance, and it's not quite making sense to begin with, then look at it and say, oh, this chlorine is attached to this carbon, and that hydrogen is clearly below the plane of the ring. That means the chlorine has to be above the plane of the ring, because each carbon has to have a group above or below. Above or below is not the same as axial or equatorial. Those are two distinctly different ways to describe the groups. So just because something's axial or equatorial doesn't necessarily mean it's above or below. And it doesn't mean it's cis or trans. So if I look at this molecule then, what I would do is I would picture myself up here looking down on the ring. Now, the ring itself is going to look like this because it'll be flat. But what we need to do is define sort of the numbering system here. So if you're looking down here, let's call that carbon 1. Okay, since the ring itself is going to be carbon 1, carbon 2, carbon 3, 4, 5, and 6. So carbons 1 and 4 are going to be the ones that's kind of behind and the one coming towards you. And then the 2 and the 3 and the 4 and the 5, we're going around the ring this way. Okay. So looking at that, what's attached to carbon 1? 2 hydrogens. We don't have to write those down. What's attached to carbon 2? A bromine. A hydrogen and a bromine. For carbon 2 here, the bromine should go above the plane or below the plane? We all in agreement it's below? If I'm looking at it from the top, it's below. So what kind of wedge should the bromine go on? It should go on a dashed wedge because it's basically away from me. And the hydrogen then would go on a bold wedge because it's above. So if we're writing a flat cyclohexane ring, the bold wedges, if my perspective is above the plane of the ring, then this is above and the dashed are below. So in this case, bromine would be below. Carbon 3, carbon 4, there's no substituents. Carbon 5, there's a chlorine. It should go on what kind of wedge? Bold or dashed? Bold. So it should go on a bold because that chlorine is above the plane of the ring. And then carbon number 6. Wait, what did I do? I put 2 4s. That's not good. So carbon 5, we've got a chlorine above and a hydrogen below, and carbon 6, the fluorine should go. The fluorine's on carbon 6 right here, the way I've numbered it. So should it go on a bold or dashed wedge? Bold? We all agree? And then the hydrogen would go on the dashed wedge. Okay, so looking at this then, the fluorine and the chlorine are on bold wedges, and the bromine is on a dashed wedge. Now you also have to be careful here of the numbering scheme, so that you could come over here and say, okay, which ones do we eliminate? I can eliminate number 2 because fluorine and chlorine in that case are trans, right? They're opposite, and that's not what we want. I can eliminate 4, so I'm down to 1 and 3. What's the difference between 1 and 3? Oh, what a piece of cake problem this is. So they didn't even move the bromine around to a different position. They just said, oh, are all 3 of them on the same side of the ring? No, that makes 3 the correct answer. Okay. Now you might say, but wait, their orientation is different. Their orientation here is different. Well, they chose a different number 1 carbon, but don't worry. I can turn this ring right here into this one. All I have to do is say, you know what? I'm going to rotate that 1/6 of a rotation. And so if I did that, then my fluorine moves to the right one. My bromine moves down 1, and my chlorine will move up 1. So all I have to do is take the molecule, take the ring, and just rotate it in the plane, and then I can line up the orientations. Okay. So your question was, why was the fluorine?
The chlorine solid.
So why is the chlorine solid but the... Yeah, so that means it's above the plane if I'm looking at it from the top. Now I could have looked at it from the bottom, but then my fluorine would be to the, if you could imagine yourself down here underneath it, looking up, then your fluorine's going to be to the left of your chlorine, not to the right of it, if you're underneath. And in that case, what I would do is I would take my molecule, I would take my ring, and I would flip it 180 degrees. Is how I would do that. Okay. What else?
So when they're saying ring flip, is it flipping 180 degrees, or is it just, how is it?
A ring flip is a totally different, flipping is a totally different context when you're doing a ring flip. You are flipping the ring, but not in that way. So if you have, and I will draw I draw my rings like this. What I say is there's a right and a left-handed version. Since I'm right-handed, this is my right-handed version. If you're left, you can decide whatever one you want, but this is the one I can draw better. There is this one that's not bad, but normally I don't get it that good. Okay, and if you're trying to draw these, so I don't know if the book has like a little hint on how to draw cyclohexanes. What you do is you start with two parallel lines. And I guess what I did this morning was I screwed it up. They should have two parallel lines where the bottom one is just a little bit to the right. So if you start with those two parallel lines where the bottom one is a little bit to the right, then you connect up the triangle there, and you connect up the triangle there, and it's perfect. Then you just got to figure out how to put your bonds in. And so I'll show you something in a minute where they call some of these things mountains and valleys. I'm not sure I like that, but anyway. So a ring flip is not moving this ring. It's not spinning it. It's not flipping it. It's keeping it in place. Okay? And so if we have to put in our hydrogens or our positions, first of all, on these three carbons that are pointed up, there are axial positions. An axial position is perpendicular to the ring. And so those three positions are above the plane of the ring, axial. So what I usually do is I'll write A for axial, and I'll just do this without color. I'll circle the ones that are above the plane of the ring. So those three are clearly above the plane of the ring. Okay. Now, the carbons that are pointed down, there's three axial positions down. And those axials then, they're still perpendicular to the ring, but they're down. So what I usually do is, if you have your colored pencils, you can, or colored whatever, you can highlight those. But below the plane of the ring, I'll just put a triangle on to begin with. So there's 6 axial positions. 3 axial up, 3 axial below the plane of the ring. Okay. And with a little practice, those are the ones that come naturally. It's the equatorial ones that are roughly in the plane of the paper that are they're harder to draw. So what you do is every carbon's got to have a tetrahedron. So that means that there have to be bonds in like a tetrahedral orientation. So if we start at this carbon right here, that's my equatorial position. And it's pointed kind of down because that is below the plane of the ring. On this one, the equatorial position is up, but it's still roughly in the plane of the ring. And so then we can go around the ring and draw out our equatorial positions. And it'll take some practice to do this, but there's my equatorial positions. And now we just have to go through and label whether those equatorial positions are above the plane of the ring or below the plane of the ring. Okay. Realizing that each carbon has to have one above and one below. And so if we start with this carbon right here, which is what I will normally call the number 1 carbon, that's just my preference. The axial is clearly above, which means this equatorial is clearly below. Down here, we'll call that carbon 1, carbon 2. The axial is definitely below, which makes this equatorial above. Over here, carbon 3. The axial is above, meaning the equatorial is below. Carbon 4, axial is definitely below, equatorial is above. And notice that I'm alternating the equatorials between above and below as I move around the ring. For carbon 5, the equatorial is below the plane of the ring, so it gets a triangle. And then finally, this equatorial is above the plane of the ring with carbon 6. Okay, so the perspective on this is that you're looking at the ring. This is carbons 2 and 3, and these are carbons. The front of my hand is carbons 2 and 3. The back of my hands is carbon 5 and 6. So you're looking at the ring like this on its side. Okay. So those are the positions axial, equatorial, above, and below. Okay. So 3 of the equatorial positions are above, and 3 of them are below. 3 of the axials are above, 3 of the axials are below. So this is how the cyclohexane really looks. Now, if you've seen, sometimes you see 6-membered rings written like this in biology. Normally there's like an O there because it's part of a sugar. If you've seen those representations, those are called Hallworth projections. And they're used in biology for sugars. They're used to make starch, to show the representation of starch. But organically, that's not how they look. Yes, they have positions above the plane of the ring and below the plane of the ring, but that ring is also in a chair, just like the cyclohexane I drew. But apparently it's oversimplified, right? And in biochemistry they do the same thing, but realize it's a chair cyclohexane. Okay. So what is a ring flip then? So once you have the positions here, a ring flip is when you convert this into this. And so the question is, how do I do that? Well, what I do is I grab this carbon right here, this bottom carbon, and I rotate it up. And when I do that, I end up with this conformation. Now, all of these are conformations. What are conformations? 3-dimensional structures that are interchanged by rotation around a carbon-carbon single bond. This is called the boat. And these are called chairs. Okay? So what you do is you rotate the left carbon up into the boat. Now, the boat is not a particularly stable conformation simply because these are called these 2 positions are called flagpole hydrogens, and in the boat, any group that's attached to those 2 positions are going to be sterically right on top of each other. And the steric, what steric means is all of these atoms are nothing but clouds of electron density. That's all the atoms are. And so if you have a group like a CH3, you've got a large collections of atoms, you've got a bigger clouds of electron density. And so the clouds of electron density repel each other, so if you get them too close spatially, they're going to repel. So that's what the steric term means in the basis for it. So in these flagpole positions, the groups are going to be really close together and repelling each other, which probably means that in that conformation, they're going to repel each other, causing the angle to kind of open up, which is what the book calls torsional strain. So we're going to use sterics pretty much as our term, and not necessarily the torsional, and not be that detailed in the definitions. So you flip it up into the boat. Then what happens is, so that just took care of this carbon. So this is carbon 1, that's carbon 1. So I just flipped that carbon 1 here, I just flipped up, so it's now over here in the left-hand version. So now what I need to do is now I need to bring that carbon down. And so down here, I'm going to bring that carbon down, we'll call that carbon 4, so that now carbon 4 is down. And so if you lift up carbon 1 to the boat, and then you bring down carbon 4, you end up interconverting the left and right-handed forms of the chair. That is what is called a ring flip, is when you go through that process. Bring the left one up, bring the right one down, and go through the boat. Although no one ever shows, people, I don't know, the boat apparently has lost favoritism. I mean, it's not a very stable conformation, but now everybody's like moving them both at the same time, so they're going through a flat conformation, which I'm not sure if that's really the case or not. But it's easy. What it's easier to do is it's easier to program that movement into the computer so you can show an animation. That much I know, because our computer science students have done that for us. Okay, so that's a ring flip.
What Gauss interactions are?
Yes, but let me finish off with the ring flip. So, okay. That's faith. Okay. Yeah, I know. Okay. Let me show you the ring flip here as an animation. Okay. There is a 99-cent app for both Android and iPhone called Chairs. And I'll write the company's name down in a minute, because I've talked to the person who owns this company and is doing the development a couple of times. I talked to her over the summertime, and she didn't tell me anything about this being in development. So this is what's called gamification. We don't do homework, we play a game. So, but I don't want to practice, I want a tutorial here. So here's my tutorial. My tutorial is, this is cyclohexane. It consists of a ring of carbons, 2 with carbon atoms adjacent to it, and 2 other atoms that are going to be the hydrogens of the other groups. But cyclohexane is not flat. The reason it's not flat is because all of the bonds for sp3 hybridization should be 109.5, and if you had a flat cyclohexane, it would be 120. That would cause the orbitals not to overlap head to head, but to overlap at askew, which would make weaker bonds. Cyclohexane is the most stable of the rings. So we can swipe up, and there it is in its chair form. I have never drawn the sun, nor have I put an umbrella on there. But that's the chair. It really should be like a chaise lounge or whatever you call those things. So chairs can flip. And so here's what the flipping is. So we bring that up. There's the boat. We bring this one down. And there's the other chair. So now it goes back and forth like this until I tell it to move forward. Those 3, that's what they call mountains. Then they have valleys. I'm not a big fan of that terminology. Whatever. But then here is where we have our equatorial and axial positions. Now, equatorial bonds are ones that are parallel to the ring, axials perpendicular. So here's the most important part. And you should go slower here, because as this goes back and forth here, if you focus on the red, and when it's pointed here, that's the one where it's up and then here is the one on the right hand. So if you look at the red is always above the plane of the ring when it does a ring flip. Okay? Red doesn't go below the plane of the ring. It's always above the plane of the ring. And the blue is always below the plane of the ring. But when we do a ring flip, what happens is the red goes from being axial to equatorial. The blue goes from being equatorial to being axial. So when we do this ring flip by lifting and pushing down, all of the positions are still above or below the plane of the ring, but now they've switched from being axial to equatorial. And so that's the important part of a ring flip. That's the important part of the ring flip, because when we draw different conformations of a cyclohexane, we need to account for the fact that a methyl group might be axial or it might be equatorial. Those are the two possibilities for that group, and any group I put on the ring. Okay? So that's what that means. So if you were to watch through this, you could see that happening here. We are not playing, we are not practicing. But that is essentially what a ring flip is. Okay. So that is an app called, at least on the, it's called Chairs. And the company's name is Alchemy IE, and they have a website, alchem.ie. This one, I believe, is 99 cents. Okay. She has funding from the National Science Foundation to put these together. And I think they're probably doing research to try and see if it helps students learn. There is another one that I'll show you that is free. And then there's other one, I don't know what the cost on that one is. That was the one she was trying to get me to use in class last fall, but I was having enough time trying to figure out how to use Top Hat properly. So it's like I can't do two things at once. Although who knows? I sat next to the Top Hat guy at the ITS fair, one of their managers, and said, "Hey, have you seen this?" And he's like, "No." And I said, "I think she was talking to your company about implementing it." And he's like, "I don't know. Let me get on the phone." I knew she was trying to get Top Hat. She was asking me for advice on how to sell it. And I'm like, "I'll show you the other one." So I don't know. Maybe I helped her along. So that's what a ring flip is. And when we do energy conformations of these, which is probably was in Wednesday's reading, that's what we have to remember. Okay. Now there is something related to it about your question, which was Gauss interactions. So in a ring, there is 1,3 diaxial interactions that are the most destabilizing. But let's take a step back and let's go to an acyclic compound. So in an acyclic compound, in an acyclic ethane, this is what's called the sawhorse representation. Okay? And there are two types of sawhorse representations. There is one where I always focus on the bonds that are in the plane, which are the regular bonds here. If you want, we can put them in red. These are the bonds that are in the plane of the screen and in the plane of your paper. There is another sawhorse representation this is sort of S-shaped. This is U-shaped. And when you have it in the U-shape, the bold and dashed wedges are both all pointing in the same direction, at least when they're attached to a carbon. So this, the one on the left is staggered, whereas the one on the right is eclipsed. That's an eclipse conformation. So the sawhorse representation then isn't very, it's not, what people found was, they found it wasn't particularly helpful in terms of trying to determine which conformation is more stable. So what they decided to do was to come over here and look down that carbon-carbon bond. And when you do that, what you will see is, you'll see a bond that's straight up and down. That's the red one. And I'll go and color it. So then you see what's called a Newman projection. So when you go over to and you can do this from the left or right-hand side. I always go to the left side and look down the carbon-carbon bond. If you do that, the front carbon has exactly the same orientation. The red pointing straight up, and then the bold and dashed off to the right or left. Then the issue is on the back carbon. The back carbon over here, that back carbon that's in the plane is pointed down, and over here the back carbon is pointed up. And so all those bonds, the bold bonds and the dash bonds, are all eclipsing. They're all in the same plane. So this is the left is the Newman projection for a staggered. The right is a Newman projection for the eclipsed. And so both of those are the Newman projections. And so those we find much easier to evaluate the energies. And they're named after, I don't know, Professor Newman, who was at Ohio State, because one of their chemistry buildings is named after him. So that's how we can tell the difference energetically. But in order to know whether it's staggered or eclipsed, you have to be able to recognize the fact that the bonds in the plane, I guess S, staggered, no, almost an E, from the side, eclipsed. That's the best mnemonic I can come up with. Okay. So with ethane, with all these groups being hydrogens, the staggered is much more stable than the eclipsed. And that's fine. That just basically means that when I have hydrogens here, when I have hydrogens on these positions, the hydrogens are nothing more than clouds of electron density, and this is as close as they're going to get to each other. If they're parallel to each other, they're right on top of each other. If I rotate them 60 degrees, then they're as far away from each other as they can get, because if I continue, I'm going to come up to the next set of hydrogens. So looking at hydrogens is boring. What we'd like to do is look at different groups attached to the front and the back carbon. So that's where, let's say that I had the molecule butane. And so butane would be adding 2 CH3s here, because now I've got 1, 2, 3, and 4 carbons. So this is N-butane. So this is just butane, the molecule. And so now butane has a whole bunch of different conformations that are going to have different energies than, let's say, an ethane. So for instance, the staggered conformation of butane could have the 2 CH3s, the one on the front and the back, in this case are opposite one another. One's pointing straight up, one's pointing straight down. Okay. And in a staggered conformation, this is what is called anti, because they're anti. They're opposite. And in this case, there really isn't any energy. The two methyl groups obviously being bigger groups than hydrogen, it's their interactions that are going to destabilize the molecule. But if they're pointed in different directions, they're not getting close together. So this is the most stable staggered conformation you can have. But I could take my back carbon here, and I could rotate the methyl group up where this hydrogen is, rotate this hydrogen over here, and rotate that hydrogen down to where the methyl is. So with each one of these Newman projections, I could grab the front carbon and rotate, or I can grab the back carbon and rotate. Never rotate both of them at the same time, because you might just be rotating your molecule and you won't get anything new. So I usually choose to rotate the back and hold the front steady. So if I did that, my front carbon isn't going to change. It's going to have a CH3, an H, and an H. But my back carbon, my methyl group, is going to come up here. Then my hydrogen is there, and my other hydrogen is there. Now, these methyl groups are still not right on top of each other, but they are now 60 degrees away from each other. This is what the book would call a steric interaction, because they basically call steric interactions anything that occurs between anything bigger than hydrogen. That's what their definition of steric is. So these two methyl groups, being now larger clouds of electron density, are going to repel each other. That's going to cause the overall energy of the molecule to go up, for it to become less stable. And so this terminology then is when you have two non-hydrogen groups next to each other in a staggered conformation, that is what is called gauche, with an E. So we would say for butane, there's only one conformation where the two methyl groups are gauche. So this is the gauche conformation of butane. For other ones, if you have more than two groups on the ring, it's not quite clear who's gauche to who. So what I could say is I can definitely say, well, these two methyl groups are gauche. That means they're in that position. They're in the 60-degree position, one on the front and one on the back. And we only talk about gauche being non-hydrogen groups that are bigger than hydrogen. So we have anti and we have gauche. And I can continue this process by taking this methyl group, and I could continue to rotate it over here, the hydrogen over there, and this hydrogen up here, which means now in my third conformation, where my front carbon has not changed, my methyl group would come over here to the left, and this is also a gauche conformation. That is also a gauche conformation. Yes. So there's two things we need to make sure we're absolutely clear on. Number one, those are two different conformations. They're two different three-dimensional structures. One has the back methyl on the right, one has the back methyl on the left. So they're the same three-dimensional structure, but, well, they're not the same. Sorry, they're not the same three-dimensional structure, but they do have the same energy. So those two have exactly the same energy, which is less than, or it's more unstable than the anti. So the anti is more stable than the gauche, but those two gauche conformations have exactly the same energy. They're not exactly the same three-dimensional structure. So that's what gauche means. Gauche means you have two non-hydrogen groups, gauche, meaning next to each other in the staggered conformation. And then for the eclipse conformation, we would do the same thing. We could put a methyl group we can put the methyl group here, and then the 2 hydrogens there, and then we could put another one of the methyl groups here. And so with the there's always 3 gauche, always 3 staggered. The 3 staggereds are always, the most stable staggered is always more unstable than the most unstable gauche. Or sorry, the most unstable stag. Let me say it a different way. The most unstable staggered is always more stable than the most stable eclipsed. So if we have 3 staggered and 3 eclipsed, and I'm ranking them, number 1 through 3 is always going to be staggered, and number 4 through 6 is always going to be eclipsed. And I don't think I found the exception to that. And if I did, I would put it on the exam. But that's, all the staggereds are always more stable than the eclipsed. And all that's based on is the interaction, the steric interaction between the methyl groups and either a hydrogen or a methyl groups in themselves. So in an eclipse conformation, you have no choice. You got to eclipse 2 groups. The best case scenario is 2 hydrogens. The worst case scenario is 2 big groups. When they're eclipsing, that's a very unstable interaction. And so the stability or the instability grows as the groups get bigger. Is how that works. Does that kind of make sense? Okay, so let me show you how we can do this one. This one will be a little bit easier. Well, we'll try and make it a little bit easier to see. All right, so this is called Model AR. And I'll write it down. But Model AR, you need to print out one of these things. So in Model AR, and I've got to somehow turn the ladybug thing here and take the cover off, because the cover covers up the camera, and that's always bad. Okay. So we have this. There. And fluorescent lights are horrible on this. No. Focus. Okay. So there's your modeler. Really? Now it's upside down. You'll get the idea. Well, you'll get the idea. Okay. Start. Okay. So what I can do when I start this is the following. Probably should. There. I grab a carbon, I bring it in. I grab another carbon, I now have a carbon-carbon bond. I'll grab a carbon and put it here, and I'll rotate it around, and I'll put a carbon there. Okay, so there is my, too many carbons. What's that? That's fine. Okay. Okay, so here's a pentane molecule. Okay. You can see that. Now I'm going to put it into, I'm going to put this molecule into Augmented Reality, which is what the AR stands for. And so what it does is it now, with that card, it's now placed my butane, it's now placed my pentane molecule above the card. Okay? So if I'm looking down a carbon-carbon bond, I'm going to look down this carbon bond. If I click on that bond, I can now rotate so that, for instance, I could put the methyl and the ethyl group here, so that if I bring them over, here's the methyl and here's the ethyl, and they are opposite each other. So this is anti between the methyl and the ethyl. I could continue to rotate now, and I could put the methyl and the ethyl somewhere here. They're not quite eclipsed, or they're not quite Gauss, but now they are Gauss. So you can see ethyl group here, and then methyl group, and then ethyl. So you can see how they're basically Gauss to each other. And so then I could continue on. The one thing this doesn't have the ability to do is to make space filling models. So AR for our model AR, and it's by the same company. And it's free. So it's completely free. And then you just have to, I'll probably end up printing a bunch of these things out and bring in the class, but if you're ambitious, all you have to do is just print this out, and then it will take the model and it'll make it that augmented. So what we need to do is we need to take these in our chairs and we need to put them together for so that we can figure out how to rank them according to energies. Okay? So that's what we'll do on Wednesday as well. So today and Wednesday are both chairs and Newtons. I have your homeworks